In our last lecture, we looked at the problem of a metal bar with an initial temperature distribution and held at a constant temperature at each end, so held at 0 degrees centigrade. And we then saw that the heat equation told us how that temperature rearranged itself as a function of distance along the bar and of time. The method of separation of variables then showed us that the solutions looked like sinusoidal functions in space and exponentially decaying functions in time, so that the long time steady state solution was just 0 degrees centigrade everywhere along the bar. In this lecture we're going to look at a very similar problem, but we're going to, instead of holding the temperature constant at each end, we're instead going to demand that no heat can escape out of the ends of the bar. That is, we're going to put insulators on the ends of the bar so that instead of the temperature being constant, we're going to demand that the slope of the temperature is constant. This is called the adiabatic boundary condition, and it's going to dramatically change the form of the solutions. So we start again with the heat equation, described by this equation right here. And we know that the temperature at every point along the bar is going to be given by the function u of x and t. This is the temperature at distance x along the bar and after a time t. Now the difference between this problem and the problem we looked at in the last lecture is a change in the boundary conditions. Specifically, our boundary conditions are not going to be on the temperature at each end of the bar, but on the slope, or the derivative of the temperature, at each end of the bar. So at x is equal to 0 and x is equal to L. We're going to use a couple of different terms for this kind of boundary condition. We're going to call it an insulated endpoint, or we're going to call it an adiabatic boundary condition. And they all mean the same thing, basically that no heat can flow across the ends of our bar. Now, mathematically that's expressed as a condition on the derivative of the temperature. Basically, we have to have a flat slope in our temperature at each end. What we'll see is that this changes our solution so that instead of all of the heat escaping out of the ends and we have 0 temperature everywhere, we're instead going to get the heat rearranged in the bar so we have a constant temperature at every point. We're also going to need to know some initial conditions, specifically the initial temperature distribution. So let's take a look at a problem like this with insulated endpoints. We've got the heat equation, we've got c squared is equal to 9, so c is equal to 3. And we've got boundary conditions at 0 and at pi. And again, these are insulated boundary conditions, or adiabatic boundary conditions. So they tell us that the slope of the temperature at x is equal to 0 and x is equal to pi is equal to 0. And we're also told the initial temperature distribution. So let's quickly sketch what our setup looks like. So our metal bar is located between a point x is equal to 0 and x is equal to pi. And we've got constant slope at each end, so I can show that with little arrows. So we're going to demand that the slope of u is 0 at x is equal to pi, and the slope of u is equal to 0 at x is equal to 0. And our initial temperature distribution is described by a function that is a step function. So it's going to be 0 up to pi over 2, and then it's going to jump up to a value of 1 degree centigrade up to pi. And so we're going to have a discontinuity. It's a step function, and we'll choose the values at the discontinuity like that. So this in blue is our initial temperature distribution, the temperature when t is equal to 0 as a function of x, and we've called this f of x, and clearly this is a step function. So we now need to look at the method of separation of variables for this problem. And as we're going to see, we're going to have to be very careful when we look at different possible values of our separation constant, k, because in fact we're going to find that the k is equal to 0 case is going to give us a non-trivial solution. So we're going to make our separation of variables assumption that u can be written as a function of x times a function of t, and we want to find the corresponding ordinary differential equations that we get. So again, we're assuming that u of x and t can be written as function of x multiplied by function of t, which means that partial derivatives will turn into ordinary derivatives. So the partial derivative of u with respect to t won't affect f of x and gives me the ordinary derivative of g with respect to t, and we're going to write that as f of x times g prime of t. We've got the partial derivative with respect to u, with respect to x, which doesn't affect g of t, but does affect f of x. And again, we're going to write that as f prime of x. Now the heat equation involves the first derivative with respect to t and the second derivative with respect to x. So we're also going to need the second derivative. And that's just going to give me f double prime. Now our partial differential equation, the heat equation, then becomes f of x times g of t, g prime of t, is equal to 9 times f double prime x, g of t. So now we're going to gather all of our t terms over to one side, all of our x terms over to the other side, and we're also going to try and keep this factor of 9 with the t terms, because we want to make the equation for f of x as simple as possible. So that's going to give me g prime of t over 9 g of t, all the t terms on the left, is equal to f double prime x over f of x. And now we can make our separation of variables argument. We've got a function of t on the left, we've got a function of x on the right, and the only way those two things can be equals to one another is if they're both equal to the constant function. So we'll call that constant k. That then allows us to rewrite these equations as two equations for g of t and for f of x. We've got g prime of t minus 9k g of t, and we've got f double prime x minus k f of x. So this looks very much like what we had before, and notice again that for the heat equation we end up with a first order ordinary differential equation for g of t, but we still have a second order ordinary differential equation for f of x. Now we need to solve for f of x, and we're going to have to do that by looking at different values of k. But first of all, we're going to have to find the boundary conditions for f of x. And remember, in this case, we're looking at the adiabatic boundary conditions, or the insulated endpoints, which is a boundary condition on the derivative of u. So let's look at what that would become. So I've got u of x and t is f times g, so du dx. At x is equal to 0 will be f prime g of t, because of course that partial derivative with respect to x only affects f. Now g of t can't be 0, because if it was 0, we'd get 0 everywhere. U is equal to 0 at all time and all space. So that's the trivial solution, which means that the only way this is going to be satisfied is if f prime is 0 at x is equal to 0. So likewise, we can look at the partial derivative of u with respect to x at x is equal to pi. That's going to give me f prime at pi, g of t, equals to 0. And again, g of t can't be 0, so that means f prime at x is equal to x is equal to pi is equal to 0. And again, we're using the fact here that g of t can't be 0. So these are our boundary conditions that we'll make use of when we're looking for solutions of f of x. So what we're going to do is, first of all, look at the case of k is a positive number. That is, k is equal to p squared. And we're going to show that it doesn't give any non-trivial solutions. So we've got k is equal to p squared. That's going to be a positive number, and we're demanding that p isn't equal to 0. We're going to look at the case of k is equal to 0 in the next part of this. So when I substitute this in for my equation for f, I'm going to get f double prime of x minus p squared f of x is equal to 0. So as usual, we assume solutions of the form f is equal to e to the lambda x, which gives me my characteristic equation for lambda. This has solutions lambda is equal to plus or minus p, which means that f of x is made up of exponentials. A e to the px plus b e to the minus px. A and b are our integration coefficients, and we're going to use our boundary condition to figure out what they are. But remember, our boundary condition is a condition on f prime, not on f. So we need to calculate what f prime is. The derivative with respect to x. So that's going to bring down a factor of p and a factor of minus p. Okay, now let's look at what happens when x is equal to 0. So using our boundary conditions, we have f prime at x is equal to 0 is going to be a times p e to the 0 minus b times p e to the 0 is equal to 0. So since p can't be equals to 0, I can divide it out, which gives me a minus b is equal to 0, or a is equal to b. And again, we've used the fact that p can't be equals to 0. We explicitly excluded that possibility at the beginning. So we have a is equal to b. We're ready now to look at the boundary condition at x is equal to pi. So a p e to the p times pi. We're going to use the fact that a is equal to b, so a times p e to the minus p times pi. And this is equal to 0. So again, p can't be equals to 0, so that gives us two possibilities. Minus e to the minus p times pi. So we have either a is equal to 0 or e to the p times pi minus e to the minus p times pi is equal to 0. Okay, so we found a is equal to 0, but that implies that b is equal to 0, which would give us f of x is equal to 0, which is the trivial solution. Or we have e to the p pi minus e to the minus p pi is equal to 0, but I know I can rearrange this, so I get e to the p pi equals e to the minus p pi, which gives me e to the 2p pi is equal to 1, which would give me p is equal to 0. But this is a contradiction, because we assumed that p was not equal to 0. So we found that there are no non-trivial solutions for the case of k is a positive number. That leaves k is equal to 0, and we're going to see that unlike the previous examples that we've seen, we are actually going to get a non-trivial solution here. So let's look at the case of k is equal to 0. In that case, we're solving the differential equation f double prime of x is equal to 0, which has the linear solution. F of x is equal to ax plus b. Now remember, our boundary condition is not on f of x, but on f prime of x, which gives us a. And notice that b now drops out of my solution. Now if I put my boundary conditions in, I've got the boundary condition at f prime at x is equal to 0 is equal to 0, which gives me a is equal to 0. And we have that the boundary condition at x is equal to pi also gives me a is equal to 0. So these two boundary conditions actually give me the same result. They give me a is equal to 0. But that leaves b. I haven't managed to figure out what b is. It remains as an unknown constant. So what we're going to do is look at the solution for g of t for the case of k is equal to 0. So going back to g of t, again, remember, we use the same k, and k is equal to 0 here. And that equation was g prime of t is equal to 0, for k is equal to 0, which also has the solution gt is equal to a constant. Let's call it c. So what we found here is that when k is equal to 0, we have the solution u of x and t is equal to f of x times g of t is equal to b times c, which is a constant. And we'll call that constant a subscript 0. And I'll put a little notation u sub 0 there to indicate that this is the case when k is equal to 0. So this is new. We found that there is going to be a solution which is just constant temperature at every point. And that satisfies my boundary condition, because my boundary condition wasn't on the endpoints of the temperature at the endpoints, but was at the slope of the endpoints. And you can see that a constant solution would actually satisfy that boundary condition. So if I was to sketch that, we've got my bar sitting between x is equal to 0 and x is equal to pi. I found some constant solution a0 that remains constant for all time and all space, and that actually satisfies my boundary conditions, because the boundary conditions were just that the slope has to be 0. That is, it has to be constant at the two boundary conditions, at the two endpoints. Okay, that deals with k is equal to 0, and we have a non-trivial solution for that case. We're going to have to remember to include that when we form our general solution at the end. But for the time being, let's look at k is a negative number. The third case, k equals to minus p squared. Again, I'm going to explicitly exclude the case when p is equal to 0, because we've just dealt with that. So my differential equation now is going to be f double prime x plus p squared f of x is equal to 0. We're going to assume solutions of the form f of x is equal to e to the lambda x, which gives me my characteristic equation. And I find my solutions are plus or minus IP, and f of x looks like sinusoids, just like before. Now again, we're going to fix a and b using the boundary conditions, but again, the boundary conditions are not on f, but they're on f prime. So I have to calculate the derivative of f of x. So that's going to give me minus a times p sine px plus a times p plus b times p cosine px. So let's use our boundary conditions. And again, these are boundary conditions on the derivative. So at x is equal to 0, substituting x is equal to 0, and here we're going to get minus a times p times sine of 0 plus b times p times cosine of 0, which leaves me with b times p. And since p can't be equals to 0, we find that b must be equals to 0. At x is equal to pi, we substitute in x is equal to pi in here, so I get minus a p sine p times pi, and this is all equals to 0, which implies that either a is equal to 0, but again that would give me f of x is equal to 0 and the trivial solution, or we have that sine p times pi is equal to 0. And we've already seen that sine of any integer times pi is equal to 0, so that tells us that p has to be an integer. So n is equal to 1, 2, 3, and so on. So we've found solutions for f of x. The only non-trivial solution will give us f of x is equal to a times cosine nx. I'm going to write little subscripts n here to indicate that this is for n is equal to an integer. Now notice here that the solutions we're getting are cosines rather than sines. We found in the last example when we were holding the temperature fixed at the endpoints that we end up getting sines, but here we're getting cosines. And we can understand this by sketching what the solutions look like. So looking at the case with the heat equation with constant boundary conditions, constant temperature, and looking at the case where we have insulated endpoints. So this is x is equal to 0, x is equal to pi, x is equal to 0, and x is equal to pi. And we'll show on the left-hand case what it looks like when we have constant temperature at the ends. So we'll call that constant temperature endpoints. And we'll call this insulated endpoints. So in the constant temperature endpoints case, we found that the solutions looked like sines, and so they satisfy the boundary conditions that the temperature has to be 0 at each end. So this was the case of n is equal to 1. We could look at n is equal to 2, and so on. So those signs automatically satisfy my boundary conditions. On the other hand, we can also look at what would happen when we have insulated boundary conditions. And remember that insulated boundary conditions correspond to there being zero slope at the boundaries. We found that the solutions look like cosines, so that would correspond to something that looks like a function that looks like that. That's a cosine, so that's n is equal to 1. Or we could have n is equal to 2, which might look something like, here's n is equal to 1. And so it's got constant slope, or zero slope, at the boundaries. N is equal to 2 would look something like that. N is equal to 3 might look something like that, and so on. But the point is that for every case, we've got a flat slope at each endpoint. In other words, we've got the derivative is equal to 0 at these points. So u subscript x derivative, equals to 0 there. And u subscript x is equal to 0 here. Notice also that, again, we get the constant solution working as well. So that would also be satisfying my boundary conditions. So what we found now is that fn of x equals to an cosine px, or cosine nx, works. And we have to go back and find g of t. Using the same value of k. So k is equal to minus p squared, or is equal to minus n squared. So the equation for g of t was g prime of t plus minus 9 times k g of t. Or if I put in the value of k, I'm going to get g prime of t plus 9n squared g of t. Again, I can look for solutions of the form g is equal to e to the lambda t, which is going to give me the characteristic equation lambda plus 9n squared is equal to 0, which gives me lambda is equal to minus 9n squared, and g of t is going to be a constant, e to the minus 9n squared t. So we can put that together now. If I put a little subscript n there, I can put that together to find my solutions. Un x of t is equal to fn of x and gn of t, which is an cosine nx, that was our x-dependent part, multiplied by our time-dependent part, so e to the minus 9n squared t. And again, I've absorbed the constant dn into an. Because, of course, we still don't know what those constants are, and we're going to have to go back and figure them out. So that's what my solutions look like. And you notice that they're cosines in space, and they're still exponentially decaying in time. So our most general solution then is going to look something like this. We've got a constant, that came from k is equal to 0, and we've got cosines that are decaying with time. Now we still need to figure out what the unknown constant a0 and an is. And as we're going to see, we're going to do that using Fourier series. So let's go back to our initial temperature distribution. It was given by a step function. F of x is equal to 0 between 0 and pi over 2, and then it jumps up to 1 between pi over 2 and pi. So if I set t is equal to 0 in my solution for u of x and t, we end up finding a0 plus the sum an cosine nx e to the 0. So e to the 0 is just 1. And that has to be the same thing as f of x. So we can immediately see that the coefficients a0 and an are going to be the Fourier cosine coefficients of f. But of course f of x is not a periodic function. So I need to take the periodic extension, and since I want to end up with a cosine series, that is an even series, I'm going to look at the even periodic extension of f. So let's take a look at what that looks like. So we're going to go between 0, pi, 2 pi, 3 pi, minus pi, minus 2 pi, and minus 3 pi. Between 0 and pi, we've got our original temperature distribution. So let's use blue for that. And that was simply a step function that jumps up at pi over 2. So we're not including that point, but we are including that point. That's our initial temperature distribution, and we call that f of x. Now we're going to take the periodic extension of this by flipping it left-right, so we get an even function. And then this is what we repeat. So we're going to just repeat this over and over until we end up with a periodic function that has even symmetry. So we'll call that the even periodic extension, f even. And as usual, the even periodic extension exactly matches our original function, f of x, between 0 and pi, which is where our metal bar is located. So we need to identify the period of this. It's twice the size of the bar. So t is going to be equals to 2 pi, which gives me that the half period is just pi. And so now I can write down what the coefficients are. A0 is going to be the average value of f of x, so 1 over 2 times L integral from minus L to L of f even dx. And we can see that that's simply going to be a half, because this is a step function between 1 and 0. So it's the average value of that. It'll be equals to a half. We also want to find the ANs. So AN is 1 over pi integral minus pi to pi f even times cosine n pi x over pi. So those factors of pi will go away. We see that f even is by definition an even function, and cosine is an even function. So I've got the integral of an even function, so I can use the fact that this is 2 times the integral between 0 and pi. And what's nice about that is that my function f of x is equal to f even of x between 0 and pi. So I've expressed everything now in terms of my original initial distribution of temperature, f of x. So that's a straightforward calculation to do. F of x is just the step function, so we can have the integral from 0 to pi over 2 of 0 plus the integral from pi over 2 to pi of cosine nx times 1. So that first integral is going to give us 0. And the second integral, the integral of cosine nx, is just going to give us 2 over pi sine nx divided by n from pi over 2 to pi, which is going to give us 2 over n pi sine of n times pi minus sine of n pi over 2. And we know that the sine of n pi is 0, so we're left with an is equal to minus 2 over n pi sine n pi over 2. And if you want, you can simplify that by expressing n in terms of even or odd values of n. So our full solution then is going to be given by the expression u of x and t is equal to a0 plus the sum from n equals 1 to infinity of an times cosine nx multiplied by e to the minus 9n squared t. That's my function of x and t. It's telling me the temperature. So now we can look at what happens to this thing as time goes to infinity. We see that this exponential here is going to cause all of those terms to decay away to 0. So all of those will be 0, but this term here, a half, is going to live on because it doesn't depend upon t. So we see that the temperature distribution, as t goes to infinity, is going to approach a half, which we see is actually just the average of the temperature the initial temperature distribution. So here's x is equal to 0, here's x is equal to pi. Our initial temperature distribution is given by something that looks like this. So this is u at t is equal to 0. And the final temperature distribution is just going to be half of that. It's going to be the average value of that. So that's as t goes to infinity. So what we see here is that the heat can't escape out of the sides of my bar. So the temperature can only rearrange itself to try and make itself as smooth as possible. And it does that by taking the temperature to be the average value. It's kind of like we've taken a bath of water where all of the water is sloshed up against one side of the bath. And then as we let it go and slosh around a bit, eventually it'll just assume a constant value everywhere. The water will be evenly distributed. So in this case, the heat is evenly distributed. And again, that's because the temperature can't escape out of the ends of the bar. So it's interesting to look at an animation of solutions to the heat equation with these insulated endpoints or adiabatic boundary conditions. I'm going to play you a little movie here of a solution to the heat equation where I'm going to put in an initial temperature distribution that's a sort of a spike, a triangle with a bunch of heat in the middle, but I'm going to demand that the heat can't escape out of the sides. So we have a slope of 0 at those 2 points. Those are called the insulated endpoints or adiabatic boundary condition, or it's also called the Neumann boundary condition, which is what it's called in this app here. So we use the term Neumann boundary condition, Neumann on the left and Neumann on the right. So the initial distribution is a triangle, as we've seen before, and as time goes on, that looks more and more like a sinusoid. But you see that that sinusoid is forced to have a flat temperature distribution at the edges. And that's going to decay away until eventually we just get a flat temperature distribution at every position and time. So that's the heat equation with adiabatic boundary conditions, or insulated boundary conditions. In the next lecture, we're going to look at the last of our partial differential equations, the Laplace equation, which tells us how the heat is distributed in 2 dimensions in the infinite time limit.